Welcome to you all to this MOOCs online video course Theory of Yarn Structure. We have completed module 1. Today we are going to start module 2. Module 2 speaks about basic characteristics of yarns. Like module 1, in this module also we are going to establish a few basic characteristics of yarn. Let us start this module with this image. What you see is a staple fiber yarn, or precisely a portion of a staple fiber yarn. As you know, a staple fiber yarn is a twisted fibrous assembly where the fibers are inclined at different angles from the axis of the yarn. So, in this image also you see a small portion of yarn, the length of this portion is L and the mass of all fibers is small m, and you see another symbol capital D that denotes diameter of yarn. So, let me repeat, this is a scheme of small portion of a yarn. L denotes the length of that portion of a yarn which is equal to fiber length, m denotes the mass of all fibers in this portion of the yarn, and capital D denotes diameter of yarn. So, the first characteristic what we are going to speak on is yarn fineness. We use a symbol T to denote yarn fineness. So, as you know, yarn fineness is yarn mass per unit length of yarn. So, here m denotes the mass of all fibers, that means mass of yarn, and L denotes length of this portion of the yarn, which is incidentally is also equal to fiber length. So, we have selected the portion accordingly. So, m by L. Now, there are different units to express yarn fineness. The one of the very common unit is tex. What is 1 tex? When the mass of yarn is 1 gram and length of yarn is 1 kilometer, we obtain 1 tex. And similarly, there are different units available to express yarn fineness. Another common unit which is available to denote yarn fineness or yarn count is any. So, is called English cotton count. When now what is any? In any, length is equal to 840 yard and mass is equal to 1 English pound. So, if we would like to convert English count to tex, then we use this expression. This all you perhaps know. There is another count unit of count available, which is called metric count. What is metric count? In metric count, length is 1 kilometer and mass is 1 kilogram. So, if you wish to convert this metric count to text, you use this conversion. As you know, text falls under direct system of counting, and English cotton count and metric count fall under indirect system of counting. There are many more expressions, units available to denote count. Right. Let us now go for the second expression, which is little unknown. So, that expression is related to substance cross section of yarn. This is a very interesting and important expression, which we do not usually follow in practice. However, for theoretical understanding, this expression is extremely important. What is substance cross section of yarn? Yarn consists of fibers, and the fibers are twisted. So, they are not straight, they are not parallel to the axis of the yarn, rather they are inclined to certain angles from the axis of the yarn. So, if we cut a cross section 90 degree at an angle 90 degree from the yarn axis, cross section of a yarn, then if we put that cross section under light microscope, probably we see an image like this, what is shown here. What do you see in this image? There are certain fibers, let us assume n number of fibers. Each fiber has a sectional area. Remember, it is not cross sectional area of fiber. As the fibers were inclined, we cut a cross section. So, these areas what you see are not cross sectional area, they are sectional area. It creates a huge difference, you will see subsequently. Now, we denote, we use a symbol star as a superscript to denote the sectional area. S superscript star subscript 1, that means sectional area of first fiber. Similarly, there will be second fiber whose sectional area will be denoted by this expression. Similarly, there will be many n number whose sectional area will be denoted by this symbol. So, in general what we see is that there will be many sectional area. Let us denote a generalized sectional area by this symbol. Right? Okay. So, if we sum all these sectional areas, then we get a quantity we will denote capital S to express that quantity. So, what is capital S? Capital S is the summation of all sectional areas of the fiber in the yarn cross section. Okay? Right. Now, what is the volume occupied by one single fiber? So, the length of this infinitely small section is d L and capital D is yarn diameter. So, the volume occupied by general ith fiber section is into d L. So, what is the volume occupied by all fibers in this infinitely small cross section of yarn? dV, which will be very small, summation dl. This dl is constant. So, we can write S into dl. Now, what is the fineness of this yarn? Yarn fineness we assume to be same in all cross section. So, yarn fineness is mass per unit length. What is mass? Mass is density dl. So, we obtain this expression. So, what we obtain is S is equal to T by rho. So, if we know fineness of yarn, it is very easily determined in a standard textile laboratory. Fiber density is also possible to determine experimentally. We will be able to find out substance cross sectional area capital S, right. Now, what is the use of this substance cross sectional area? We need to understand this. To answer this question, we have to little go back to the definition of yarn fineness. You remember, we define yarn fineness by this: T is equal to mass per unit length, right. Now, what is mass of yarn? volume occupied by fibers, say capital V, into density by L. So, this T by rho is equal to V by L. Now, this expression gives a very important message to all of us. What is that message? We generally perceive that yarn fineness talks about size of a yarn. How much fine is the yarn? How much coarse is the yarn? Imaginatively, we think yarn fineness talks about the size of the yarn, but this is not correct. Why it is not correct? Because of this expression. If you look at this expression very carefully, then you will see that volume by length, this is an expression which generally denotes the size of an object, which is not equal to T, rather which is equal to T by rho. That means, it is possible that a yarn of same fineness, a yarn of a given fineness T prepared from lighter fibers, say polypropylene, whose density is relatively low. So, a yarn of a given count prepared from lighter fibers may be larger than a yarn of same count prepared from heavier fibers, say viscose, whose density is higher than the density of polypropylene. I repeat, if V by L denotes the size of yarn, then it might be possible that a yarn of a given count T prepared from lighter fibers, say polypropylene, may be larger than a yarn of same count prepared from heavier fibers, say viscose. That means, these two yarns, their fineness or count are same, but their size will be different. One will look larger, one will look smaller, but the traditional expression of yarn fineness capital T is not able to talk about this. That means, when we compare the size of yarns, it is better we use this expression V by L, not T. What is V by L? V by L is equal to T by rho. That means, if two yarns are given, if we know their fineness and also if we know the fibers which were used to prepare those yarns, so we will calculate this ratio, very simple, T by rho. Then numerically higher value of this ratio, size of that yarn will be higher, larger. And just now you have seen that this S is equal to T by rho and T by rho is equal to V by L. That means, substance cross sectional area is a very important quantity which we will talk about yarn size or size of yarn in a geometrical manner. So, that is the importance of substance cross sectional area of yarn. That means, if somebody will ask, there are two yarns which size is larger, quickly you need to calculate capital S. How? T by rho. Then the yarn which will have higher value of capital S will be larger than the yarn which will be having smaller value of capital S, which will be smaller. So, what we learned now is that yarn fineness is probably not a good characteristic to compare size of yarns. Substance cross sectional area is a better quantity to characterize the size of yarn. So, by now in this module, two characteristics we have discussed, one yarn fineness, second substance cross sectional area of yarn. Third, we are going to speak about substance diameter. Here d is not substance diameter, but d is yarn diameter. Then what is substance diameter? So, we are going to speak about substance diameter. These two terms, substance cross sectional area of yarn, substance diameter of yarn, these two terms were probably first coined by Johansen. He was a scientist, devoted his life in solving problems related to yarn structure. He coined for the first time these two terms. These two terms we often do not speak about, however, they are very, very important for theoretical understanding of yarn structure. So, let us come back to this, what is substance diameter. You see here two images, one a typical cross section of yarn whose diameter is capital D. So, capital D is yarn diameter. Okay. Now, let us compress this yarn from all sides isotropically, so that the air which was present inside the yarn is completely removed. So, we are going to compress this cross section so that the air is completely removed. Then probably we will find out an image which will be looking like this. So, there is no air, all fibers are touching each other. Here the image is circular and the diameter of this circle is ds. So, here ds is called substance diameter. How will you find out substance diameter? What is the area? This area is equal to capital S, substance cross sectional area, and the circle. So, pi times ds square by 4. So, ds is root over 4 times s by pi. And what is s? S is T by rho. So, all are measurable quantities. Capital D, yarn fineness, very easy to measure. Rho, fiber density, is also possible to measure. So, ds is possible to determine substance diameter, right. Now, in all practical purposes, substance diameter of yarn is smaller than yarn diameter, real yarn diameter in all practical cases, right. So, we will now introduce a relatively new term called relative fineness. Fineness everybody knows. What is relative fineness? Relative fineness we define by the ratio of yarn fineness by fiber fineness. So, yarn count direct system divided by fiber linear density. Some of you may think at this moment that capital Y T by small t is the number of fibers present in yarn cross section, is not it? Probably during your undergraduate course you have learned this expression, number of fibers present in yarn cross section is equal to yarn count direct system index divided by fiber fineness index, is not it? This is not correct. Why they are not? Why it is not correct? Because fibers in yarn are not straight. They are inclined at some angles. So, if you calculate number of fibers from this expression and if you measure actually number of fibers in yarn by using some cross section cutting technique, you will find that this number will be always higher than experimentally determined number of fibers in yarn cross section. We will speak about this today in a little deeply. So, that is why we call this expression by relative fineness. Now, let us further work on this expression in order to know more about this. What is capital T? Capital T is substance cross section area into fiber density, we have just now derived, and in the last module we have derived that small t fiber fineness is fiber cross section area into fiber density. So, what do you obtain? Capital S by small s. Now, what is capital S? Pi ds square by 4 divided by pi d square by 4. What is ds? Substance diameter of yarn, and what is small d? Diameter of fiber. So, we finally obtain this expression, right. Okay. We will answer to this question. If this is not true, then what is true? That means, how do we find out number of fibers present in cross section of yarn? We are going to answer this question, but before that we need to understand about one more important characteristic of yarn structure. which is known as coefficient K n. It is another relatively new term probably for you, coefficient K n. What is coefficient K n? K n is a coefficient, we define it by a ratio of fiber cross sectional area, small s is area, this you know from first module. And what is this term? This is mean sectional area of fiber. How to find out it? What was the total sectional area? Capital S divided by n. What was capital S? We have already derived it. Is not it? So, the definition of coefficient K n is probably clear. It is a ratio of cross sectional area of a fiber to the mean sectional area of fiber. How to find out mean sectional area? Substance cross sectional area of yarn divided by number of fibers present in yarn. This we do not know yet. Well, now let us find out an expression for K n. What you see here, two images, is not it? This image, what is this? This is basically scheme of a fiber which is inclined at an angle theta I from yarn axis. There could be n number of fibers. We are talking about one general fiber, that is why we use this subscript I. I can be 1, I can be 2, I can be n, I can be any number. So, this general fiber, ith fiber, is inclined at an angle theta I from yarn axis. Okay. Now, this fiber has a sectional area S subscript I superscript star. And we use two quantities, dl is this length and dxi is this length. What is this image? In this image we express the cross sectional area of the fiber, that is S. So, if a fiber is inclined, if you cut along this you get sectional area, but if you cut perpendicularly along this you get cross sectional area S. Is that clear? Now, what is the volume of ith fiber? Volume of ith fiber is sectional area into perpendicular height. This is equal to the cross sectional area into perpendicular height. These two will be equal because both are volume of the same fiber. So, S into dxi by dl. What is this? This is equal to cos theta I. So, this cos theta I is equal to dl by dxi, right. Then what is capital S? Capital S is the sum of all these areas for n fibers. So, summation I is equal to 1 to n S by cos theta I. S is a constant, it can come out of the summation. Right. Now, so we come back to this expression now. S star is S by n. So, this is S divided by n. Right. So, what is Kn? Kn is from here S by S star bar. So, if you substitute S star bar here, this S and this S will be cancel out, and as a result what we will obtain is 1 by n summation 1 by cos theta I. Right. So, this is the expression for Kn. Let us learn more about this expression. So, the quantity Kn is the harmonic mean of the inclination angle theta, right. Well, second, if theta is 0 for all fibers in the yarn, that means all fibers are parallel to the axis of the yarn, then it is not a yarn, it is a parallel fiber bundle. So, if theta is 0 for all fibers, then it becomes a parallel fiber bundle. In that case, Kn will be equal to 1. So, Kn will be equal to 1 for parallel fiber bundle. In all other practical cases, Kn is less than 1. Right. Now, just to tell you a few facts, Kn is typically equal to 0.95 for cotton ring yarn. and Kn is equal to typically 0.8 for rotor yarn. Okay. So, coefficient Kn is clear now. Now, we come to another characteristic of yarn, that is related to number of fibers in yarn. Number of fibers present in yarn cross section. I told you a few minutes before, n is not equal to this. Then what is the correct expression for n? Let us find it out. N is S by this. How? We have already used this expression. So, n is this. Let us now write capital S by small s into small s by small a star bar. Right, you can write it. Now, what is this capital S by small s? Capital S by small s, you remembered, tau is capital T by small t, that is equal to capital S into rho, this into rho. So, capital S by small s. So, this is equal to tau. And what is this? Small s by a star bar, Kn. So, n is equal to Kn times capital T by small t. It is not because Kn is less than 1 for yarn. If Kn is equal to 1 for parallel fiber bundle, then this expression is correct. Right. So, I told you, if you use this expression to find out number of fibers present in yarn cross section, you will get a higher value than the number of fibers present in yarn determined experimentally. Right. So, now this expression can also be used to find out Kn experimentally. How? Kn is n by this. If you cut a cross section of a yarn by using microtome and all other apparatus and put that cross section under microscope, you will be able to find out, you will be able to count how many fibers are present. So, n you will be able to determine experimentally. Capital T, yarn count, yarn fineness, you will be able to determine experimentally. Small t, fiber fineness, you will be able to determine experimentally. That means, these 3 quantities are possible to determine experimentally. Then by using this relation you will be able to find out Kn. Right. So, in this manner we will be able to find out coefficient Kn and also number of fibers present in yarn cross section. As I said you, typically Kn is very close to 0.95 in case of cotton ring yarns. However, because of the disordered arrangement of fibers in rotor spun yarn, Kn is equal to roughly equal to 0.8. Okay. So, now we will go to discuss another important, rather very important characteristic of yarn structure, that is called packing density. Now, probably I told you that in yarn structure we study the arrangement of fibers in yarn. This arrangement is generally expressed either expressed by fiber packing arrangement as well as fiber directional arrangement. Fiber directional arrangement means fiber inclination from yarn axis. This coefficient Kn will be able to speak about fiber directional arrangement, fiber orientation in yarn. How do we find out fiber packing arrangement? How to characterize fiber packing arrangement in yarn? By using packing density, we can characterize fiber packing arrangement in yarn. What is packing density? We use a symbol mu to denote fiber packing density. Fiber packing density is a very important characteristic of yarn. We will use in many modules this term packing density. Packing density is defined by volume occupied by all fibers in the yarn divided by volume of the yarn. So, packing density is a ratio which is defined by volume occupied by all fibers in the yarn to the volume occupied by the yarn itself. Now, what is your V? Volume occupied by all fibers in the yarn. In this module we have already learnt V by L is equal to T by rho. So, V is equal to T times L by rho. And what is Vc? Vc is pi d squared by 4 into L. If we consider yarn is cylindrical, we often consider it. Right. Now, what is T by rho? T by rho is equal to capital S, also we have learned. So, T by rho is capital S into L. Into L. So, this L will cancel out, we will obtain S by pi d square by 4. Now, what is S? S is T by rho. So, T pi d square by 4 into rho right. So, mu is equal to S by pi d square. Further we can write it as pi d s square by 4 by pi d square by 4. So, d s by d whole square. So, this is an expression for mu. So, mu is defined by this expression, volume occupied by all fibers in the yarn divided by volume of the yarn. We can, if we know this expression d s and d, we also will to find out what is mu. Now, we would like to learn packing density a little more. This is a very important characteristics of yarn structure. We are going to use it in many modules. We should have a more feeling for this term packing density. Now, let us learn this term a little more. Now, in fact, this term packing density is probably very important for almost all textile materials, be it a monofilament or sliver or yarn or woven fabric, knitted fabric, non-woven fabric, very important term. So, this table gives you an idea of the level of packing density in different textile materials. In monofilament, there is no air, practically there is no air. So, packing density of monofilament is 1. Limit structure we will come a little later. Combed cotton yarn, packing density ranges from 0.5 to 0.6. Carded cotton yarn, packing density ranges from 0.38 to 0.55. What is the packing density of roving, cotton roving? Lot of air is present, packing density ranges from 0.1 to 0.2. What about sliver? What is the packing density of sliver? It is a very porous object, packing density is typically around 0.03 for roving. What is about woven fabric? Packing density of woven fabric is 0.15 to 0.3. Knitted fabric typically ranges from 0.1 to 0.2. Cotton wool is a medical product we often use to cover a wound. Packing density ranges from 0.02 to 0.04. Some other materials, just to compare where our textile material falls: earthenware 0.2 to 0.23, wood 0.3 to 0.7, animal leather 0.33 to 0.66. So, this is a table which gives you ideas about the packing density in different materials. Now, packing density, now if somebody will tell you packing density of this yarn is around 0.5, what do you infer from this information? You will tell that from definition 50% of the volume is occupied by fiber, 50% of the volume is occupied by air. Very good, correct. Can you speak something more on this? Can you talk about the arrangement of fibers inside the yarn? is a little difficult. Let us have a try. What is the meaning of structural meaning of packing density? Now, probably you have heard during your undergraduate course hexagonal packing arrangement, hexagonal model of fiber packing arrangement in yarn. So, we will use a model of fiber packing to know more about this term packing density. So, circular fibers, let us assume, let us imagine that circular fibers are arranged in a hexagonal manner in a yarn. So, this is typically hexagonal arrangement and its unit cell is a triangle which is shown here. Now, what is the packing density of this structure? If we are able to find out the packing density of the unit cell, that will be equal to the packing density of the structure, because this structure consists of this unit cell. So, it is an equilateral triangle. So, this equilateral triangle packing density, you will be able to find out area occupied by the fibers, by area of the triangle. What is the area occupied by the fibers? So, this is the area of this sector. There are 3 sectors. So, this is the area occupied by the fibers, and what the formula of equilateral triangle into D plus H, this is the base. So, you see that square, right. Yeah. So, what is H? H is the distance between 2 fibers and D is diameter of fiber. Now, so this is the expression for packing density in hexagonal packing arrangement. Now, in the next class we will find out 4 variants of this arrangement by considering different values of H. We will try to find out packing density of those 4 variants, and then we will be able to find out which is typical variant for yarn, because we know yarn packing density ranges from roughly 0.4 to 0.6. So, which of these variants follow yarn structure we will be able to know. Also, we will be able to know what is the meaning of packing density 0.5 or 0.4 or 0.6. So, in the next class we will do that. Thank you very much for your kind attention.